going on. Let's try to solve a lead code problem. This problem is called longest increasing subsequence. In this problem, you will be given an array, so you will have to return what is the possible maximum increasing subsequence length. So here the increasing subsequence is 2, 3, 7, 101, or you could just take 18. This is the longest possible increasing subsequence. You can see that 901 is also, but it is not the longest. So you will have to return the longest length possible. So let's try to think of how we can solve this problem. So you will have to solve this problem in order of n squared time. Could you improve it to order of n log n? We will see that in the later part of this video. So let's try to think of an idea. So the basic approach, the naive approach to solve this problem, is to generate all the possible subsets out of this array and see what are the increasing subsequences there, and only keep those and then take the maximum length out of it. But this is not a great solution at all. This would cost us an exponential time complexity. So can we solve this in order of n square? Well, we can use dynamic programming for this. So in order to solve any problem using dynamic programming, we will have to think about two things. One is the sub problems, overlapping sub problems. Overlapping in the sense that the sub problem will reappear again and again in the computation, so we can memorize those results and just reuse that. And optimal substructure. Optimal substructure is a property by which we can determine whether we can actually solve this problem using dynamic programming or not. But how? If we can somehow combine the aggregate the result of the sub problems to solve this problem, to solve the actual bigger problem, then we are good to go. So let's try to do here also. So my idea is to take each element as the last element of the increasing subsequence and see what are the numbers which is less than equals to that number. So if that were the case, then I'm dividing this problem into let's call it DPI. DPI is our actual problem. So DPI is basically max length of increasing subsequence ending at I, index I. So we will just then keep dividing that all the possible index where the number is less than or equals to nums I. So if that's the case, then we will take that sub problem's value. So we will take let's call it as m, n, and some other indices. So there could be multiple possible sub problems. So but the question is, this is the overlapping sub problem, but the question is how we can combine this result. If we take max out of it, then we will be able to solve this dynamic programming problem. So again, let me just summarize the idea. So we will start with any number and we try to do that in the backward direction, that what are the numbers which is less than or equals to that number. So we will just see what if that were the last number of the longest increasing subsequence, or what is the value of that sub problem, plus 1, because we are increasing, we are just actually considering this number as the last number. Okay, it might be confusing. Let me just summarize the idea here. DPI will be max of all DP j equals to 0 to I minus 1, where nums I is greater than dpj. So if we need strictly increasing subsequence, then it will be greater than, otherwise we can just go with greater than equals to. So in this problem we need strictly increasing subsequence. So let's go with this. And what is the base case then? So the base case is when the length is 1, when initially in this DP array we will fill up that all the entries with 1, because the base case is when there is only one number in the array, or in the array segment, then that is actually forming an increasing subsequence itself with having a length of 1. So that will be the base case. Now let's try to solve this problem. I'm gonna define max length as initially as 1, because 1 is the possible length when there is only one element which is have if yeah, that's the base case. And let's take length as nums dot length. All right, so let's declare our DP array. So it will be of length. Now what we will have to do is we will have to initialize this array with all the entries as 1 initially. So that's our smallest possible sub problem. Now I'm gonna start from the first index itself, not 0. It will be clear in a moment why I'm not starting from 0, because from 0 there is no possible way to go back actually. So if I take the first index, then I can just iterate from the 0th index to one index less than this. So let's try to do that over here, and j would be from 0 to I minus 1. So what I need to check here is dpi will be maximum of dpi and 1 plus uh, dpj. So but when we should check this, if we should check this when nums of I is greater than nums j. Otherwise we cannot actually get an increasing subsequence by considering the jth number as the previous number. So again this will only update the dp array. We will have to also update the max. So for that we will take max length as maximum of max len and dp I. So that's it. It's now time to return some value. So what we are gonna return is if length is equals to 0. So if the length is equals to 0, then there is no possible subsequence, but we have initialized max length as 1. So this is one of the corner case, so it will be 0. Otherwise we can simply return max length. Let's run this code. Okay. I'm going to submit this. Okay, it's accepted, but it's only 32% faster than all the submissions. Can we do this in order of n log n? Just think of it. Yes, we can do that. If we use an height balanced binary search tree and keep adding the increasing elements, then we can do that. But the question is how. Let's try to think of it. So I'm gonna get rid of all of this stuff from here. Okay, so what I'm gonna do is I'm gonna use tree set. So tree set in Java is height balanced binary search tree, which uses red black tree. So I will write a tree set. Let's call it tree set of integer, which is tree. It will be all right. So this is our height balanced binary search tree, and we will iterate all the numbers from this array, and we will see if any number which is greater than or equals to this number is present at the array. So our goal is to keep adding the number in increasing order. So let's say that 10, 9. So initially if we find 10, so initially we will add that number to the binary search tree, then 9. So our goal is to keep adding the numbers in increasing order, but if we find that the current number, if we find that there is already a number which is greater than or equals to the current number, then we will remove that number, because we want to because this number is also be part of the increasing subsequence, but we would like to keep the lowest number possible in the list. Why? Let's try to see with an example. Let's say that this is the tree that we already have. I'm talking about a tree after in order traversal, because in order traversal gives result in sorted order. Just think of in this way. Let's say that this is our increasing subsequence, and we get a number. Okay, let's make it 5. We get a number 4. Now if we get an such situation, then 1 2 3 5 is the increasing subsequence. Also 1 2 3 4 will also be an answer. So in this case we would like to just keep the lowest possible number, because if we keep that, so then we can extend our sequence to furthermore, and that will give us the best result. So let's just do that. So but how we can search the number which is greater than or equals to this number in the binary search tree? So for that there is an operation called ceiling operation. So ceiling operation takes a value which is num in this case. So if it finds the value, it will return the value, otherwise it will return null. So if x not equals to null, then we will remove the number from our tree, and at last we will add this value to our binary search tree. So at the last, our tree dot size will have the number of elements in the longest possible subsequence. So let's try to run this code. All right. So you can see a lot of improvement in the time. Now let's discuss the time complexity of this approach. So inserting an element in the tree will cost us order of log n, and deleting an item would cost us order of log n. So that, and this loop will be executed for n times. So n multiplied by log n plus log n, which is 2 log n. So basically this is order of n log n. Okay, so that was it. If you like this video, please like, comment, share and subscribe. Thanks.